In modern medicine, the devastating spread of abnormal cells is a story we hear almost daily. You likely know someone affected by tumors in the lungs, the breasts, or the colon. Yet, in the midst of all this, there is one major organ noticeably missing from the oncology ward. You almost never hear about a patient battling cancer of the human heart. This diagram illustrates that staggering gap. Out of all documented cancer cases, primary heart cancer accounts for less than 0.1%. To put that in perspective, reviewing 1,000 autopsies typically reveals only a single instance of a primary heart tumor. The muscle that works harder than any other in your body, beating roughly 100,000 times a day, is effectively shielded from the body's deadliest biological failure. The heart possesses specific biological and physical traits that the rest of our anatomy lacks. These traits turn the very mechanics of life into a barrier that cancer struggles to penetrate. To understand the heart's defense, we have to look at how cancer starts. At a microscopic level, cancer is a glitch in cellular reproduction. It happens when a cell divides to replace itself and makes a fatal mistake in its genetic code. Every time a cell splits, it rolls the genetic dice. Organs like your skin or colon are constantly shedding dead cells, meaning they roll those dice millions of times a day. Look at this timeline comparing standard cells to heart cells. While most tissue constantly multiplies, heart muscle cells are terminally differentiated. After birth, they stop dividing. Instead of splitting to grow, existing heart cells simply increase their physical volume. By opting out of the cellular replacement cycle entirely, the heart removes the risk of that genetic glitch. No division means no dice rolls. This biological refusal to replicate is the primary reason tumors almost never originate in the heart muscle. But that only explains why tumors don't start there. What happens when cancer originates in another organ, like the lungs, and uses the bloodstream to invade the heart? Recent research provides an answer. A study published on April 24, 2026, revealed that biology is only half the equation. The other half is strictly mechanical. The interior of the heart is in a state of perpetual violent motion. It forcefully circulates 5 to 6 liters of blood every minute. The sheer hydrodynamic power of that constant flow, combined with the continuous contracting of the muscular walls, creates a highly hostile environment. A stray cancer cell attempting to latch on is immediately swept away by the current. Trying to establish a tumor inside the heart is like trying to plant a fragile seed on the hood of a car driving 100 miles an hour through a hurricane. Furthermore, the heart sits securely inside a protected chamber. Unlike your lungs or your skin, it isn't exposed to outside carcinogens. It is bathed exclusively in circulating, filtered blood. So even if a malignant cell sneaks past the biological freeze, the heart's unrelenting kinetic energy acts as a physical shield that obliterates its chance to take root. Between a biological freeze on cell division and the brutal mechanical wash of the circulatory cycle, the heart operates behind an impregnable dual-layer defense. The rest of our organs remain vulnerable. Researchers are now mapping the exact genetic signals and mechanical forces that define the heart's stability to see if they can be replicated elsewhere in the body. As you can see in this pathway model, the medical objective is transferability. If scientists can isolate the exact conditions that keep heart tissue stable, they could theoretically apply that immunity to highly susceptible organs like the liver or lungs. Researchers are currently hunting for those specific markers. The goal is to develop a way to trick vulnerable cells into adopting that same terminally differentiated state the moment they are threatened by a mutation. The heart's constant motion sustains life and provides a physical barrier against malignancy. This dual-layer defense offers a roadmap for protecting the rest of the human body.